Okay, so today we're just going to review solving all different types of equations. Prior to Algebra 2 last year, really the only types of equations you knew how to solve were linear and quadratic, and then maybe some absolute value from Algebra 1, but I'll just assume that most people forgot how to do that. It's been so many years. But then in Algebra 2, we kind of added on rational functions, radical functions, polynomial functions, so we'll review some of that today so that they're all mixed together. I think first and foremost we'll talk about, anytime we get to a problem here, identifying it for what it is. So these first two are rational because they've got variables in the denominator. And the rational rule is to get a common denominator on every single term, and then once you do that, you can cross out those denominators and solve as normal. Before you're getting a common denominator, always a good idea to factor, because you'll realize that probably some factors are already in common. So this factors into x plus 6, x minus 2. Sure enough, now that already has everything it needs. This guy just needs an x plus 6. This guy just needs an x minus 2. So they all have x plus 6, x minus 2, so you can get rid of that, and now your equation just comes from the numerator. So I'll distribute that 3, distribute the positive 1, which doesn't really do much, equals 4, and then we'll just solve it to become a linear. 4x equals 4, and then x equals 1. And then with the addition of these more complex equations last year, all of a sudden this idea of extraneous solutions comes up. So you always want to check your answer, not so much for accuracy like you used to do, but just to see that it's not extraneous. We'll assume we did everything right, obviously, but then you would plug back in the number and it wouldn't work because of some bizarre issue. Now with rationals, what would have been an extraneous solution would have been negative 6 or 2, those excluded values, and we did not get one of those, so that should work. Okay, and number 2, just this one factors into x plus 1, x minus 1. This one needs an x minus 1. This one needs an x plus 1. Then we can get rid of our denominator. So 1 times x minus 1 is just x minus 1 equals 2. And then be careful here because we have a negative. So we're actually distributing a negative 1 to the x plus 1. Negative x minus 1. And then if we get all our x's, I'll put them on the left. I get 2x. Get my non-x's, add 1 over to the right. I end up with 2x equals 2, and I get x equals 1 again. However, that is an excluded value. If we go up here, that would make each of these denominators 0, which is a problem. So this actually has no solution. That's called an extraneous solution. Okay, in exercise 3, these are called literal equations. And literal equations are ones that have multiple variables in them, so you're not going to get an answer like, in this one, solving for p. You're not going to get p equals 7. You're going to get p equals some expression in terms of these other variables. So p will equal something that's dependent on q and f. So it's a literal equation for that reason. It's also still irrational just because we've got the variable we're solving for in the denominator. So just like a rational equation, common denominator all the way across. So this one needs a q and an f. This one needs a p and an f. This one needs a p and a q. So PQF, 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 they've all got it. So when I get my equation for my numerator, I get QF plus PF equals PQ. Now this is tricky. I'm solving for P, and right now I have P in 2 locations, both on the left. Now if this was a 3P and a 4P, it would be real easy. I would just subtract this one over and combine like terms. I'm still going to subtract them over because I need all my p's together if that's what I'm solving for. The problem is I can't really combine them because they're not nice numbers. And if you had me last year, maybe you remember this, but my going phrase is if you can't combine them, can't combine the p's, factor them. So in other words, factor out the p. as a GCF. Now my problem only has one p in it, and that has to be the way it works out. If you're solving for a variable, that has to be the only variable in the problem. So we started with two of them. We had to kind of condense them and factor out that p, so that now there's only one. And then you just get that p all by itself by dividing away the q minus s. So you get p equals qs over q minus s. This one is probably just a linear equation. There's no variable in a denominator, but we're solving for b. And right now b's locked up in a set of parentheses. So we have a couple options. We could distribute the 1/2 h, or we actually could just divide by 1/2 h on both sides. Now, we typically don't divide by a fraction. We would instead multiply by 2. That'll take care of the 1/2. And then we can divide by the h. So we have 2a over h equals a plus b. So because we kind of whittled away at what was outside of the parentheses, now those parentheses aren't necessary anymore because we divided that h way and divided that 1/2 way. So the a plus b is now kind of free. We're solving for b, so we're just going to subtract the lowercase a from both sides. 2a over h minus a equals b. And there you go. B is solved for. So absolute value equations, again, it's been probably about 3 or 4 years since you've done this. This one is simpler in the sense that the absolute value is already by itself. That needs to be step one, is to get the absolute value expression isolated. So here, we're going to have to add the 15 over and divide the 5. But this one's already isolated. So then what I'm going to do is I'm going to kind of cover up what's inside those absolute values with my pencil and pose the question, what number could be underneath my pencil that would make this true? So the absolute value of what number, or I should say numbers because there's two options, the absolute value of what numbers equals 1. And you should be thinking, well, it could be the absolute value of 1, because that would equal 1, or it could be the absolute value of -1. So this particular expression could equal 1, or, and I call this kind of like a branching step because there's two mini equations that we're going to have to address, or this expression could equal -1. And so from here, you've kind of applied the concept of the absolute value sign. So you notice once you branch off, the absolute values are gone. And then you'll just solve each mini equation. So if I add 1/3, I'm going to think of this as 3/3 plus 1/3 is 4/3. And then multiply both sides by 2. So x equals 8/3. That's one solution. On this one, I'm going to add 1/3. And again, here I'm going to think of this as -3/3 plus 1/3, which is going to be -2/3. And when I multiply both sides by 2 here, x equals -4/3. So two solutions there, which is common for absolute values to have two solutions. If you think actually about what an absolute value graph looks like, you should know it's got somewhat of a V shape to it, and when is it going to equal 1, so wherever the 1 level is, it should make sense visually why there are usually two solutions. Okay, so on this next one, isolate the absolute value. Divide by 5. So now we have 1 minus 4x in absolute value sign equals 3. So I'm not going to go through the concept again, but essentially what you do is you take your expression, you set it equal to 3 as one branch, and you set it equal to -3 as the other branch, because this expression could equal 3, and the absolute value of it would work out to be 3, or that expression could equal -3, and then the absolute value of it would work out to be 3 as well. So we'll solve that, subtract 1 from both sides, -4x equals 2. So for that we get x equals -2/4, or -1/2 as one solution. And over here, subtract 1, Negative 4x equals negative 4, so x equals 1. And then with these two, you guys look out for extraneous, so you would plug back into the original and just make sure they work, and I do believe all those will. Alright, and lastly for today, polynomial functions. So this one's a cubic polynomial. This one's a quadratic. So quadratics we've been doing for years. Definitely since Algebra 1 with solving by the quadratic by factoring or by the quadratic formula. Whereas cubics and fourth degree polynomials and all of that, we really just got to for the first time last year. These pretty much have to be done by factoring. So once you get it equal to 0, and again that part's nicely done for you, you want to try to factor. This one has 4 terms. Take out an x squared, I'm left with x minus 4. Take out a negative 4, and I'm left with x minus 4 in the second group, so grouping worked. So one of the terms is x minus 4, the other is x squared minus 4, and then I can just factor that one step further. So I get x equals 4, negative 2, or positive 2, and I tee it up. Now, with this quadratic, I would first try factoring. If I do a quick test, if I'm looking for two numbers that multiply to get 2 and add to get negative 6, which there's no way that's going to happen. So if you can't find the two numbers that would split the middle term nicely, then it's not factorable. So if it's not factorable, the other option is the quadratic formula, which you're not going to be given anymore, so you definitely need to know negative b plus or minus the square root of b squared minus 4ac all over 2a. The Regents reference sheet has been giving you that all these years. I'm not really sure why. Definitely something you should know. So we all should know, hopefully, that a is 2, b is negative 6, c is 1. So the opposite of b, the opposite of negative 6 is 6, plus or minus the square root. I always recommend squaring b on your own before you put it in here, simply because it should always be positive, and lots of times I'll see people write negative 6 squared, which is technically wrong if they forget to put the negative 6 in parentheses. So just square that b term. Negative 6 times itself is 36. It should always be a positive number there. Minus 4 times your a of 2 times your c of 1. All divided by 2 times your a is 2 times 2 is 4. And then we'll just simplify. So 6 plus or minus the square root. This is going to be 36 minus 8, which is 28 over 4. We reduce the root 28 because it's root 4, root 7, so it'll become 2 root 7. And then if the two coefficients up top and the denominator share a common factor, which they do, of 2, then you can reduce all of them by 2. So that would be 3 plus or minus root 7 all over 2. So I've essentially divided each one of those by 2 and taken out that common factor. And those are your solutions. So your homework from the worksheet will be, let's just stick with our 1s, 3s, and 7s.